So our first set of exercises for alcohol reactions looks at relative acid-base strength. And we know that we can approach problems like this either by looking at the strength of the acid or the strength or weakness of the corresponding conjugate bases. In our first question, we have two phenols, and the only difference is the presence of this silicon group on the second compound. Silicon we find on the periodic table directly below carbon. And if it's directly below carbon, it's going to be less electronegative than carbon. Well, if it's less electronegative than carbon, that makes silicon into an electron donating group. As an electron donating group, electron donating groups in general destabilize conjugate bases. By destabilizing the conjugate base, we make the conjugate base stronger. If the conjugate base is stronger, then the corresponding acid is weaker. So by adding the electron donating group, phenol here becomes a stronger acid because it doesn't have the electron donating silicon group. In part B, we have two alcohols. Both alcohols are attached to 3 carbons. The difference is the arrangement of those 3 carbons. And so in the first compound, isopropanol, we have 2 methyl groups directly attached to the carbon with the alcohol. In 1-propanol, our compound on the right, there's just a single carbon group, and while it may be bigger, the fact that it's only 1 carbon group that's directly attached to the carbon with the alcohol means there's less electron donation taking place, and therefore a stronger acid. And part C is in many ways just like part A. We have 2 phenols again. The difference in these 2 phenols is the substituent. Now, both methoxy and amino are groups that have both electron donating as well as electron withdrawing properties. They're both electron donating when we look at resonance. Both are electron withdrawing when we talk about electronegativity or inductive effects. So now it just becomes a question of which one has stronger effects. And the oxygen, because it's more electronegative, does a better job as a withdrawing group. Because of that, it also does a poorer job as a donating group. And so overall, the oxygen is the more withdrawing group and gives us the stronger acid. Part D is very similar, but probably a bit more straightforward. Fluorine, being the most electronegative element we have, is a highly electron withdrawing group and does a good job of helping to stabilize the conjugate base, which means it comes from a stronger acid. In part E, we have an example that can benefit from drawing our resonance structure, or our conjugate bases. When we do that, we can see that the compound on the right has an anion that is stabilized by resonance. The compound on the left does not. Because this is resonance stabilized, So because this is resonance stabilized, that means it, as a conjugate base, is more stable. If the conjugate base is more stable, that means it comes from a stronger acid. Right. For question 2 here, we have a series of reactions, and we're trying to predict the major products for these reactions. So as we know, it's important to know what each of these reagents do, and then see how that applies to the situation that we're given. So sodium borohydride is a reducing agent, and it works best for reducing aldehydes and ketones to alcohols. So we do have an aldehyde in this compound, and so sodium borohydride, it won't touch the alkene, but it will reduce that aldehyde into an alcohol. Our next part, we have Jones reagent. Jones reagent is an oxidant, and we can have two possible products depending on the type of alcohol that we start with. For Jones reagent, if the alcohol is primary, then typically we're going to end up oxidizing twice all the way to the carboxylic acid. If, however, the alcohol is secondary, it can only oxidize once, and we end up with a ketone. Here, this alcohol is primary, and so upon reaction with Jones reagent, we will get the two oxidations all the way to the carboxylic acid. Our third reaction, we can see that we have an alcohol in the presence of aqueous acid and heat. These are conditions that lead to elimination, and specifically, this is going to be an E1 elimination. We know it's going to be E1 because of the reaction conditions. The alcohol elimination typically requires acid and doesn't work as well under E2 type conditions. It doesn't work under those conditions because the OH group is generally a poor leaving group. So by adding the aqueous acid, we can convert it to OH2 plus, or water, as a better leaving group. Also important, because this is E1, you may recall that when we're dealing with six-membered rings, sometimes we have to worry about the geometry of the leaving group and the proton that's being removed to make sure we have the right orientation. But that's only for E2. Since this is an E1 reaction, it doesn't matter. Now we have two carbons that are adjacent to the alcohol that both have hydrogens on them. But in this case, it doesn't matter. The entire molecule is symmetric, and so it ends up not mattering which of those two carbons we remove the alcohol from. And so we end up with an elimination product. Our next example is a ketone being reacted with LAH. LAH is a strong reductant. As we will learn later on in the course, it will reduce any carbonyl that it comes in contact with. And in almost every case, that reduction will happen all the way down to the alcohol. Next, we have another example with Jones reagent, but this alcohol is tertiary. And you should recall that tertiary alcohols, they don't have a proton to give up, so they cannot be oxidized. And since they can't be oxidized, Jones reagent won't do anything here. Now, as opposed to Jones reagent, where Jones reagent gives us different products based on whether we're starting with a primary or secondary alcohol, PCC, which is a more mild oxidant, doesn't give the full oxidation up to the carboxylic acid. So if we're starting with a primary alcohol, it only gets oxidized a single time, and we end up with the aldehyde as the product. Why is that? Well, you may recall that with Jones reagent, which uses aqueous acid, that resulting aldehyde gets converted to a hydrate, and that hydrate can be further oxidized. Since there's no acid present in this reaction, there's no ability to convert this to the hydrate, and if we can't convert it to the hydrate, it can't react any further, and so we stop at the aldehyde. On the other hand, in this next example, as we said, Jones reagent with an alcohol, primary alcohol, will oxidize twice to give us the carboxylic acid. Sodium borohydride, as we mentioned in the first example, reduces aldehydes and ketones to alcohols. And then we end with another attempt to oxidize a tertiary alcohol, this time with PCC. But regardless, we can't oxidize tertiary alcohols. Again, there's no proton, no hydrogen to remove, and so the reaction doesn't work. So our final question on this exercise is to provide a mechanism for the oxidation of benzyl alcohol to benzaldehyde. And we're going to do that with PCC. So it'll start out, it'll benefit us if we draw out the structure of PCC. And I'm just going to draw the chromium piece, because we don't really need to look at the pyridinium piece in order to go through this mechanism. Now that chromium, being bonded to all those oxygens, ends up functioning as a good electrophile, and our alcohol in the benzyl alcohol can attack it, and that'll force some of these electrons up onto oxygen. So I'm going to abbreviate the aromatic ring since it's not substituted with anything other than the chain with the alcohol. We're just going to abbreviate it as pH here. From here, one of these negatively charged oxygens adds its electrons back in, kicks out the chlorine. Anything that can function as a base at this point, even the Cl- we just lost, can remove that hydrogen. And what we've managed to do at this point is to put a leaving group onto oxygen. And if you notice, this last step is going to look very much like an elimination, just creating a carbon-oxygen bond, carbon-oxygen double bond, instead of a carbon-carbon double bond. But again, any species that can function as a base can come in, remove this hydrogen, swing these electrons up, and kick out the chromium leaving group, and we get our product.